In this video, we will take a look at the three different types of ionizing radiation: alpha, beta and gamma radiation. This topic is very much linked to the stability of nucleons and nuclear physics, which we discussed in last week. Therefore, we will also need to discuss nuclear decay, which is a stochastic process rooted in the underlying quantum mechanics. Due to the complexity of the underlying quantum mechanics, we will discuss this topic in a more simple context. But quantum physics is indeed what is behind nuclear decay. As we will see later, to get the full picture of the different decay processes, quantum mechanics is actually not good enough, and we must study quantum field theory. But we will come to that later. In general, it is all about stabilizing the atom, or in other words, the goal is to reach a new and stable state of lower energy. To start off this discussion, let's start with something most people, if not all, encounter at school: the periodic table of elements. This is an organized table with different elements that humans have managed to observe. A key term here is element, and that refers to the number of protons in the nucleus. It is this number which relates to the properties of the given element. Now, the important part is that there are different types of isotopes of each element. Thus, for example, you can have hydrogen with 0 neutrons or hydrogen with 1 neutron. This is also called deuterium. Both these atoms are hydrogen atoms, but there are different isotopes of hydrogen. Thus, each element can have many different isotopes. So the type of isotope of each element is determined by the number of neutrons. The periodic table just reflects the most common isotopes on Earth. This is because most isotopes are unstable and decay, thus only a small set of the isotopes of each element are stable. Lead is the heaviest element to have a completely stable isotope. All heavier elements are unstable. This leads to nuclear processes and decays. Regardless of what type of decay we consider, the equation for the decay is the same. If you have enough amount of some radioactive substance, then you can calculate how much of your substance has decayed after some time t using a rather simple equation that states that n is equal to a naught e to the power of minus lambda t, where n is how much of the substance that remains after some time t. Lambda is the decay constant, and it is different for each element and isotope. The decay constant lambda is related to the mean lifetime tau in the following way. Tau is equal to 1 over lambda. Another often used number is the half-life, T-half, of an isotope. This constant is related to the decay constant in the following way. T-half is equal to ln2 divided by lambda. The factor of ln2 comes from the fact that the decay is not linear, and the first half decays much faster than the second half. If we rearrange, we get the following equation in terms of the half-life. N is equal to n naught times 2 to the power of minus t over t half. If we have 1 kilogram of tritium, which is the hydrogen 3 isotope, and wait 10 years, we can calculate how much is left using the fact that the half-life is 12 years. If we plug in the numbers, we get that 56% will be left after 10 years, or around 560 grams. Having discussed radioactive decays of isotopes, we can look at the different radiation which comes from these decays. In general, decays are a result of the atoms being in an unstable state, and it needs to undergo some change to minimize the energy in order to reach a stable state. To remove energy, it can radiate ionizing radiation like alpha radiation. This is the most energetic of the three, but actually not that dangerous for humans, as we will discuss later. Alpha radiation is when an unstable nuclei sends out a helium nuclei, thus a nuclei with 2 protons and 2 neutrons. This process changes the nuclei into another lighter nuclei. Thus the atom actually changes to another element, which has 2 protons less. An example of this process could be plutonium-239, where plutonium-239 via alpha decay change into uranium-235 plus the alpha particle. An interesting fact about alpha decays is that they actually would not take place without quantum mechanics. In particular, quantum tunneling is essential for this process to occur. Essentially, it's like the opposite situation compared to fusion. In alpha decays, the alpha particle uses tunneling to escape the nuclei. Another type of radiation is beta radiation, and this is less energetic than alpha radiation. This is because the alpha particle is much heavier, and as Einstein learned, mass and energy are related via the mass-energy equivalence principle E equal to mc squared. The particle emitted in beta decays is either an electron or positron, which is the antimatter particle of the electron. We will discuss antimatter in more detail in the future, but since the electron is around 8,000 times lighter than the alpha particle, it is just less energetic, even though it generally has a higher velocity. Beta decays occur when a nuclei either changes a neutron into a proton or a proton into a neutron. This is called beta minus decay and beta plus decay respectively. At the fundamental level, the beta decay is a bit complicated and it involves the weak force, but the general idea is rather simple. A beta minus decay can be written as follows. The neutron N turns into a proton plus an electron plus an antineutrino. We see that a neutron turned into a proton. In this process, an electron is emitted, which is the beta decay particle. There is also a neutrino involved, and this is another fundamental particle which we will discuss in a later video. The beta plus decay can be written in a similar way, but let's just finish the discussion on the beta decay with an example of how cesium-137 undergoes beta minus decay. We have that the cesium-137 decays into barium-137 and emits an electron and an antineutrino. Note again how the beta decay also changes the identity of the atom, but only by one proton. The last type of radiation is gamma radiation. This type of radiation occurs when a nuclei is excited, or in other words has excess energy. In this case, the atom simply sends out an electromagnetic gamma ray, which one can consider a very high energetic photon. But because the photon is massless, it is still less energetic compared to the beta particle. But note that the range is much longer. An example of this would be when cobalt-60 decays into nickel-60. Due to a beta decay, the nickel atom is excited and will then emit gamma radiation according to the following equation. Excited nickel-60 turns into relaxed nickel-60 plus a photon or a gamma wave, which is sent out like radiation. Note that in gamma decays the atom does not change identity, but simply loses energy. When it comes to nuclear processes, you generally always have radiation, and with radiation comes safety issues. Each element and isotope is different. Some are stable and some are not, and the unstable ones decay. The type of decay each atom can undergo is different, and sometimes it can undergo different types of decay. The important part is to protect yourself from whatever radiation you deal with, so let us discuss how to protect yourself. As mentioned earlier, alpha particles are the most energetic, but because the alpha particle is so big, it is generally not harmful because of two reasons. Its range is short and it can be blocked by even a thin sheet of paper or just your skin, so unless you eat it or get it inside you somehow, then it's not dangerous. Beta decay is a bigger health issue as it can penetrate your skin and do damage to you. It can however be stopped by metal, so it is rather easy to contain a source of beta particles, but you should avoid getting hit by beta particles. Gamma particles do not hit very hard, so to say, but if you get a high dose, it's still very harmful. The issue with gamma rays is that they are almost unstoppable. One of the best ways to stop them is a thick layer of lead or a lot of concrete, though stopping them fully is hard. Because gamma rays are so hard to stop, they are often more scary, even though they do less damage per hit. While radiation can sound intriguing and scary, we should remember that it is natural. We live in a world where radiation is around us, and as long as we don't get exposed to large quantities, the effects on the human health are insignificant. One of the good things about radiation is that it can easily be measured using a Geiger counter, so you know when you are in danger. This cannot be said about other biological hazards like viruses, etc. Such hazards are much harder to detect and avoid, therefore remember to be careful with radiation, but do not fear it without a reason. As always, I hope that you learned something new. I now have a support page at Buy Me a Coffee, so if you wanted to give me a tip, check out the link in the description. Otherwise, please comment, like and subscribe. See you in the next video. Stay tuned.